Hi, chemistry students. We have one last slide, couple of slides, but we're getting a little stuck here. All right, the last gas law. All right, so we have seen Charles' law, Gay-Lussac's law, Boyle's law, Avogadro's law, Dalton's law, right? We can kind of review them all here. We've seen all of these different things. They're in the videos. We've practiced Boyle's law, inverse relationship, pressure and volume. Charles' law, direct relationship, volume and temperature. Gay-Lussac's law, direct relationship, pressure and temperature. Avogadro's law, direct relationship, volume and moles. All right, so now we're looking at our last one, the ideal gas law. If we put all of these laws together, all right, we can kind of mix them up. We can get this equation. PV equals nRT. This is the ideal gas law. This is the top of your knowledge of gases. PV equals nRT. All right. At football games, this should be a chant in the crowds. PV nRT. Right. Pivner. You'll hear people say it. PV equals nRT. All right. This is pressure times volume. Pressure times volume equals number of moles times the gas constant times the temperature. All right. All of the other gas laws we've seen, they were a before and after scenario. All right. You have this pressure before you change the temperature. What is the new pressure at this new temperature? The ideal gas law doesn't have a before and after feature, right? There's no two pressures or two volumes or anything. It's a more right here, right now, right? If you have this pressure in this volume of a container and this many moles, this is what your temperature must be. Or if you have this many moles at this temperature in this given volume, this is what your pressure is going to be. All right. It's 4 parts: pressure, volume, number of moles. We'll also call that amount, and temperature. The gas constant is a constant that never changes. And in every question, you will always be given 3 of them. I don't know which 3 you'll be given, but you'll always be given 3 of the 4, and you'll be solving for that 4th. All right, so PV equals nRT. That R, that gas constant, it is 0.08206. All right, and R has units. It's liters times atmospheres divided by Kelvin times moles. And the reason it has these units is to get both sides of the equation to have the same units in the end. All right, so if you think about it, pressure times volume, those units are liters times atmospheres, does not equal the units of mole times Kelvin. So R fixes that. And R can change if we use different units, but I decided, why don't we just all agree to always use these units? We will always use the liter, we will always use the atmosphere, we will always use Kelvin, and we will always use the mole, and that way we won't have to learn extra R values. It'll just always be 0.08206 for us, and that would be really nice. Now, kids get tripped up by the units. Just promise me you'll always use atmosphere. Pressure is the big unit that changes a lot. As long as you always use atmosphere, don't even worry about the units. R is 0.08206. All right, so let's go through one practice problem. It's a pretty straightforward equation, the ideal gas law. And again, it is our last piece for this gas law unit. So we'll see a few questions on it. So let's look at this practice question. You have 10 moles of a gas at 30 degrees Celsius, occupying a container which is 0.5 liters in size. What is the pressure of this gas in atmospheres? All right, so something to think about. You're given moles, you're given temperature, you're given volume in liters. You have been given 3 out of the 4. You're asked to find what is the pressure. So pressure is our unknown. All right, and you have 3 of the 4. There's no change happening. If we go back and read this question, you have 10 moles of gas at 30 degrees Celsius. Yes, that at connects them, but I don't see any change happening, right? We're not heating it up, we're not cooling it down, we're not compressing it, we're not moving it to a new space, right? So it's not changing, right? So it's this right here, right now. You have 10 moles of gas at 30 degrees Celsius in a 0.5 liter container. What is the pressure, right? Given 3, solve for that fourth one. All right, now units wise, moles is in moles. Moles are moles. Moles are moles are moles are moles are moles. The 30 degrees Celsius, that we need to change to Kelvin. And we do that by adding 273. Not a hard problem. Volume is 0.5 liters. That's good. And pressure, when we solve for our final answer, will be in atmospheres. So we don't have to do anything there. All right. So we're going to add that 273 to the temperature. And then we're just going to plug in everything, right? Ideal gas law. PV equals nRT. P, we're going to make X because we don't know what it is. V is 0.5. So X times 0.5. All right. If we were in school, maybe I'd be yelling at you to make sure you write the L next to the 0.5. But for right now, with our digital learning, you can just leave it just like that, 0.5. So X times 0.5 PV equals N, 10 moles, 10, R, 0.08206, our constant, T, 30 plus 273, 303, right? So X times 0.5 equals 10 times 0.08206 times 303. I would simplify the right side of the equation, all right? And then I would divide by 0.5, so you get X by itself. X is going to be 497 ATM. And this answer should make sense. All right, we're going to get a large pressure because I want you to think about something, class. We have a lot of gas in a very small space. It's going to be colliding with the walls a lot. And it's not like it's really cold. It's actually a pretty high temperature. So a lot of gas moving really fast in a really small space, yeah, that's going to give us a big pressure, 497 ATM. All right, so this is the ideal gas law. It's the last gas law. We've seen everything with gases now. I want to remind you, temperature is how fast the particles are moving, and that's always in the unit Kelvin. Volume is the space it occupies. We like to think of that in liters. Two types of containers. Balloons are flexible. They can change their volume, all right? And rigid containers, something like a steel canister, rigid, does not change its volume, all right? Pressure is the number of collisions inside of a container. There is always outside atmospheric pressure pushing back, so that's why balloons can expand as they rise up in the atmosphere because the atmospheric pressure decreases, so the balloon is able to expand, all right? And moles is just the amount, the number of gas particles inside the balloon, and they all come together in the ideal gas law. PV equals nRT. So now you have watched this video, and now you know everything that you need to know about gas laws. All right, you are done with this unit, so that's got to feel good. All right, so take care, guys.